Hi everyone, my name is Geanderson and today I'm going to talk about my paper Failure of One, Fall of Many, an exploratory study of software features for defect prediction. This paper was developed by me and Professor Eduardo. Our presentation is divided into 5 topics: the introduction, methodology, feature implementation, experimental results, and final remarks. The introduction. The motivation to doing this work is, first of all, predicting software defects is important to anticipate software bugs. Also, the defect prediction problem is still open as we do not have a machine learning model that can explain every single defect for every single programming language. For this reason, we want to explore the features that indicated the defectiveness of Java projects. To do so, we compare the accuracy and variability of these features with the model selection. Methodology. Our methodology was divided into 5 steps. First of all, we executed the data selection where we had to select a data that could represent the defect prediction task. After selecting the data, we went to the data exploration. Here, we executed, for example, data cleaning, feature engineering, correlation analysis, and so on. After exploring the data, we went to the data modeling. So, modeling was important because we could develop machine learning models that could predict software defects. It's important to say that all the models were subject to the same setup. After modeling, we went to the explainability. Here, we use a concept called shape values to try to explain why our model has made such predictions or why our model has predicted that a software is defective. And finally, we have the results of our paper. It's important to talk about our data. Our data was part of the MSR competition a couple years ago. The dataset is called the Bug Prediction Dataset. It has 5,371 classes and they are all part of the Java programming language. These classes are divided into 5 projects, and after data exploration we end up with 37 software features. All of these features, they are part of the CK matrix, and these features, they are divided into entropy, change, and class level. Here we can see the distribution of our classes within the projects. For example, here we can see that some projects had more classes than others, or some projects had more defects than others. Feature implementation. Our model generation approach was based on the classic XGBoost algorithm. We apply a random search to enumerate the best combination of features. After randomly selecting the features, we pick the best performing combination based on an evaluation metric. In this case, we use the ROC curve AUC to evaluate our models. Finally, we were able to create over 250,000 models using this approach. Experimental results. Here, we are comparing our approach to previously applied machine learning models. For example, from 1 to 8, we can see some machine learning models such like logistic regression, SVMs, decision trees. Our approach is called USXGB, standing for unbiased search. We are not sure about this name because this is more like a random algorithm than unbiased, but we can see here in the AUC numbers that if they are not the best, they are very comparable with the baseline algorithms. It's important to say that all of these algorithms use the entire set of features, but our approach uses a limited set of features from the pool. And also we are reporting only the AUC here, but in the paper you can check the F1 score as well. In terms of predictive accuracy and variability, we plot these metrics in these two graphs. Here you can imagine that every x-axis here represent a feature. So here we have 20 features. We do not have 37 features because we apply feature selection with feature importance here. So we can see that some features have a very high accuracy, for example, close to 90%, but they drop to 82, 81% as they go. And in terms of variability, we use MAD, and we can also see that the features they drop from a higher variability to a very low variability. It's important to know that the feature age, which is measured by weeks, is the feature that had the highest accuracy and the lowest variability when counted by the weight age. In terms of trying to explain the defects in our data set, we use the concept called SHAP. So here, taking as an example two projects in our data set, we can see that our model was able to explain the defects using up to 4 features. So that was the highest number of features that we use. And in some projects, we were able to explain the defects with only 2 features, as in the case of the Lucene projects. This graph is not so hard to understand. So, for example, if you take as an example the code churn here, so the red indicates that when the number of code churn is high, as in the case of this line, it means that our model is more able to predict a defect. So we can apply the same logic to all the features here. So some of the implications of our work for developers: first of all, our algorithm could assist the development of a tool to classify Java projects. We are already working on this tool. We found out that change metrics are more likely to yield higher accuracy than other metrics. As I said before, we apply this work to change metrics, entropy, and class levels. So we found out that the change metrics are more likely to yield higher accuracy. In terms of explaining software defects, we found out it is a project-specific task, so we could not expect a model to predict every single defect, as they differ for each project, at least in the language Java. And we found out that the feature age measure in weeks appear in our explanations, and it yield higher accuracy numbers than any other features. So maybe we should work more with these features in the future. So the final remarks. In terms of detecting software defects, we realize this problem is a really hard problem, as using certain techniques to machine learning, we could not achieve over 87% accuracy for any of the projects. In terms of the features that we use to predict these defects, we realize that a limited set of features achieve high AUC numbers. That's interesting because not all the features are actually important to predict software defects, and the accuracy they achieve, they vary greatly. In terms of the collection of features, they also vary greatly within the models that we created. So for certain models, they use certain types of features, and other modules, they use other features. And another interesting result is that the best models are actually simple to understand, as they are composed by only up to 4 features, and for example for the Lucene project it is composed by only 2 features. In terms of future works, we are working on a tool to classify Java projects into defective prone. That's one of the work that we are doing in terms of working on the many variations of the algorithm that we are using to select the features. We are also exploring more techniques to explainability. For example, in this paper we use a black box technique represented by SHAP, but there's other techniques in the literature, for example, glass box techniques. So maybe in future iterations of this work we are going to compare these techniques in terms of explainability. We are also planning to classify software features prior modeling, because maybe classifying these features it's going to be easier for developers to understand the models explaining with SHAP. And finally, we are planning to investigate the feature age in other contexts, because this feature achieves higher predictive accuracy than any other software feature that we analyze in this paper. Finally, we have some provoking questions for this session. First of all, do you think the age of a class measured by weeks is a key factor for the defectness? As we showed in this paper, this feature was really important to predict defects, and actually it was the best feature to predict defects. But what do you think about this feature? The second question is, do you think the target programming language would change the results of our paper greatly? For example, in this paper we just use Java. What about if I use C or Python? Do you think the results would be different? Thank you everyone.